Okay, let's go ahead and get started with our notes. We're going to go over functions today and relations and get a good idea of what's going on with those two and make sure that when this is all over that you guys know how to tell what a function is, what makes a function, and more importantly, what's the difference between a function and a relation. Okay, so a relation is described as every x value, which is also known as the input. It's also called the independent value. Every x value is matched up with at least one y value, which is the output. What I'm going to say here is basically that a relation is technically everything. Every time you see an ordered pair, every time you see an x value and a y value, no matter what, no matter how repetitive it is, let's see, you have 1, 7 and 1, 2, and let's say we have another one where it's 3, 7 and negative 3, 7, and everything you see is absolutely a relation. It can be, basically, if you can chart it out on a coordinate plane and put a point there where it has an x and a y value, if you could put it anywhere on the coordinate plane, then you're dealing with a relation, as long as you can do that. If you're only given an x, or if you're only given a y, then you're not going to be able to make a point. I mean, you're going to be able to kind of figure out approximate location on the x and y axis, but not exactly where it is. A function, however, is really the overarching topic that we're going to talk about today, which is each x value. And the thing that you want to really concentrate on here, each x value is matched up with exactly one y value, one and only one. And I should also point this out, that a relation says at least one, but function, what makes that different is that it's only one. It's exactly one y value. I think the definition, however, for a function is a little bit confusing, and it makes perfect sense once we start kind of jumping into some examples here. And let's kind of look at some arrow diagrams here where we have some x values, and they're not really called x values. They're just called the domain, but we can think of them as the x, and we have our range, which is our y values. And in this example here, this is a real life example here, we're looking at the name of the game and the console that matches up with it. And we want to describe, like, is that, what we're looking at there, is it a function or is it not a function? What I'm going to do is I'm going to go ahead and match up the game with the console that it exclusively is played on. So for instance, Halo is only a product of Xbox. It'd be great if it was on PS4, because I loved playing Halo when I had an Xbox system back in the day. But nope, it's only on Xbox, that's it. Animal Crossing, which is, I think, all the rage right now. My kids want a Switch just so they can play on Animal Crossing, is just for the Switch. And then God of War, which is a terribly good game. I'm not sure if you guys are familiar with it, but I know many people that really love God of War on the PS4. So, but those are exclusively games. Halo's exclusively a game for Xbox. Animal Crossing is for New Horizon. That is definitely for Switch, and God of War is only for a PS4. And the thing that you might want to notice is if you look at all these arrows here, if you look at all the arrows, if you look at all the vectors that are coming out of the domain, there's exactly one vector coming out of Halo, there's exactly one vector coming out of Animal Crossing, and there's one vector coming out of God of War. So that is definitely a function. We're looking at a function here because we could say that there's exactly one member of the domain that matches up with a member of the range. There's one x value, exactly one x value. Halo does not, you cannot play Halo on a PS4. You cannot play Halo on the Switch, or at least I don't think you can. I'm pretty sure it's Xbox, but if I'm wrong, I'm sure I'll hear corrections in the comments. But that would make it not a function. I mean, it still is a relation. It's a relation and it's also a function, but more importantly, it's a function. In the next example here, I just wanted to throw an example where maybe it's a little bit different. And if I kind of do the same thing, Halo, again, not much is different Halo is played on the Xbox. Animal Crossing is a Switch product. God of War is PS4. Rocket League is PS4. Rocket League can be played on Switch, and Rocket League can be played on the Xbox. And the thing that you might want to kind of look at here is if you look at all those vectors that are coming out of Rocket League, there are 3 arrows coming out of that. So that is definitely not a function. Not a function. Now, the opposite of a function is not a relation, because everything's a relation. But you can at least call it a relation. If it's not a function, you can at least call it that. But when you have more than one arrow coming out of anything of the domain, then it's not a function at all. I put a vending machine, and I don't think you can see the letters really well, but the example I like to, when I'm in school at least, the example that I always like to show is for a function. The example that I always like to show for a function is the vending machine example, which, if you put yourself in the shoes of a vending machine owner, if you own that vending machine, then you want a functioning machine. A functioning machine is working, it's putting out a product. When someone presses a button or a series of buttons, they get something that drops down and it's theirs. All right, now let's talk about what will make this not a functioning machine, or maybe, in your eyes, what's going to make it so that it's not profitable? So one thing that I did here is I just changed some of these things. I know most vending machines are not going to be like this. Okay, so I went ahead and just kind of put in some numbers in there. You guys, I'm sure you're all familiar with how a vending machine works. Let's say you wanted to buy this bag of Fritos right here, that bag of Fritos, and you push the button A1. Well, if you're the coder for this machine, you did a pretty terrible job because you assigned several rows the A value. So there's an A value there, there's an A value here. So there's 3 different rows in that machine that has an A, which screws everything up. Because now when you push an A1, if you do that, well, that bag's going to come down. So is that. All right, and whatever that, I'm not sure what that is. In that vending, I just kind of took a picture off Google Images, but that's going to drop down. So obviously, yeah, jackpot, that's going to be a win for you. You're getting more things for your money. That's great. As a consumer, you're like, yes, I get extra stuff, extra food. But like I said, if you put yourself in the shoes of the vending machine owner, then this is not a profitable machine. Your vending machine is putting out too much product. That's not what you want to happen. Obviously, if you're a kid and all of a sudden 5 things drop down out of the vending machine, that is awesome. That's great, but not for the purposes of being, not for the purpose of making money. If you want to make money, then you better fix this. You better get rid of some of these values and recode that machine, make sure everything's working. All right, and got some more examples here. Now, these are just examples that you can go through. If you want to go through them and kind of pause the video and go through them on your own, go ahead. Okay, now that I drew my arrows there, you can probably figure out what it is. And what did you guys think it is? Did you guys think it was a function or not a function? And the answer to this would be not a function. Not that cars should function in the literal sense, but we're talking about mathematically, if I were to say, hey, I saw a Ford on the road, well, that's not very descriptive. There's a ton of different Fords. It's a Ford like F-150, there's a Ford Mustang, there's a Ford Focus, there's a Ford Escape, I think. And there's a lot of different Fords out there on the road. So, let's say I was trying to tell the police officer, hey, I know a Ford was involved in the accident. Well, that's not going to function as a good description for the model of the car. So I need to be able to kind of give a better description of that. But this in and of itself is not a function. I always think this is kind of an interesting question right here, which when I teach this in class, I always pose this question, which is, and there's not a lot of information here, but if the domain is people in a doctor's waiting room, let's say it's like you and your family, or just you and just 4 or 5 strangers, it doesn't matter, is the weight of the people in the waiting room, is that a function of the people in the waiting room? So I'll give you a second to think about that. You can pause the video and let me know what you think. Okay, so if you unpaused it, here's how I always pose it, which is, okay, let's say the people in the waiting room, I'm just going to make up some names here. We've got Mike, we've got Amy, we've got Steve, we've got everyone's favorite name, Karen. We've got those people in the waiting room. Let's say we've got the following numbers. Let's say we've got like 180. Let's say we have 120, 350, and I only have 3 numbers there. Now, what do you think? Now, if I only wrote 3 numbers there, do you think that's a function, or is it not a function? It's definitely a relation no matter what, but is it a function or is it not a function? Am I leaving off not enough information? Is it possible that these 4 people, Mike, Amy, Steve, and Karen, is it possible that they could all share these weights, 180, 120, and 350 among the 4 of them? And the answer to that is, yeah, they could. So let's say, like I said, let's say Mike is 180 pounds, and I'm just making this up. These are all made up people. Amy is 120 pounds. Steve is 350 pounds. And Karen is also 120 pounds. So that is okay. Now that is a function. If you were to just focus on the domain, if you look at the vectors there's exactly 1 vector coming out of Mike, there's 1 arrow coming out of Amy, 1 out of Steve, and 1 out of Karen. And that's all that matters. If you just focus on that, I can usually when I'm teaching this in class, I can cover my hand up. I'll cover the range up and you'll just look at the vectors. But if you do that, if you just cover up the range with your hand and just look at the domain, you're seeing only 1 arrow coming out of every person. And that's all you need to know. So just to make a point here, I mean, I could have put 1 weight in the range column or in that range circle, and we can still have a function here. So we can do this. We can have, all right, Mike is 200, Amy is 200, Steve is 200, and Karen is 200. So that is still a function because, like I said, if you look at all the arrows, there's only 1 vector coming out of every person. That is how that works. And let me just show you why there's no way for this possibly not to be a function. Because let's say we have 120 again, like some of the similar weights that I had before. I don't know if those were before, but let's say, Mike is 120, Amy is 150, Steve is 200, Karen is also 200, and Steve is also 120. Does that make any sense that Steve, is Steve going to weigh in and one time at 120 on the same day, the very minute that he weighs in at the doctor's office? Is he going to weigh in at 120 and the scale is also going to say 200? Is that possible? No, that would be a malfunctioning, non-operative scale. That would just like I'm talking about the vending machine, that scale would not be functioning if it gave me 2 different weights for Steve. So that kind of, I like those real life examples of what makes a function and what doesn't make a function. It perfectly explains why it is a function and why it's not. Because I think it gets a little bit abstract, especially with the next example that I'm going to show you, where it's just numbers. So for a function or a relation, one thing I really haven't talked a ton about, which is domain and range. And go ahead and copy down these notes, but domain is all the x values. And here's another thing we're going to talk about. They're also called independent values, known as inputs. The range is basically all the y values. And those are known as the outputs, which are considered dependent values. If we look at this arrow diagram, we'll see that, just look at the way the arrows are connected. I've got 0 connected to 0. So I'm going to write that as an ordered pair. I have 1 connected to 4. That's an ordered pair. We have 2 connected with 2. And 3 is connected with 0. One little cheat too is like, sometimes if you don't have an arrow diagram, because arrow diagrams are out of one single domain, you know it right away that it's a function. But if you look at this, you might notice that, there's not a single x value that repeats itself. Now, you could basically just ignore the y values, But if you just look at the x values, there's only one 0, there's only one 1, there's only a single 2, and there's only one 3. If you notice any repeats, if there was another 1, if there was another 2 or something, then that would not be a function. So this, again, we're talking about a function. Now go ahead and do this on your own. Pause the video, and when you're done, just see if your answer matches up with mine. So what do you guys think? Is this a function or not a function? If you said it was not a function, you're correct. It's not a function, and you can tell that. I mean, you probably didn't have to go much farther than this. You notice that there's a 0, 4, and there's a 0, 0. So we want exactly one member of the domain to relate to one member of the range, and that doesn't happen here. We have 0 that relates to 4, and we have 0 relating to 0, so that does not work. Graphically, if you look at the picture, you see there's 2 vectors coming out of 0, and that's an instant tell, and it gives it away right away. Now, the last thing I want to talk about with functions, the difference between independent and dependent values. If you can think back to when we were graphing, I know we go over a lot of stuff in algebra, but if you think back to when we were graphing linear equations, and one of the first ways I taught you how to graph a linear equation was to just make up, and I told you guys, like, just make them up, just off the top of your head. Make up some values for your x's. And I said that was okay. You can just totally make those numbers up whole cloth and just, off the top of your head, just make up those values. But then those values had to be plugged into an equation. You know, let's say the equation was y equals something really simple, like 3x minus 1. Then those values had to be plugged in. So if I plug in 0, I get 3 times 0 minus 1, which is negative 1. If I plug in 1, I'm going to do 3 times 1 minus 1, which is going to be 2. If I plug in 2, as you can see, I get a different value. So 3 times 2 minus 1 is going to be 5, and so on and so forth. That kind of goes to show you that the x values are independent. Independent meaning, like, they could be anything. They kind of stand alone, and you can just kind of put them in and make them anything you want. Whereas the y values are dependent. These numbers depended on the function. They depended on that function of 3x minus 1. So I just couldn't make those numbers up. I totally made up these numbers. Sorry if this is getting messy, but I totally could have made up those numbers. But these numbers depended, hence the name dependent. Those numbers depended on the x values, the independent values. And so, like I said, here's some just real life examples of independent or dependent values. And I want you guys to let's go through these, and what do you guys think? For these examples right here, I want you guys to tell me which one is the independent value and which one is the dependent value. Let's look at this. So we have height. Is height dependent on age, or is age dependent on height? Now just think about that. Is height dependent on age? I mean, at my age, I'm not growing anymore. I'm probably shrinking at my age. But the height at your age, I would definitely say that the older you are, the taller you're going to be, right? The younger you are, the shorter you're going to be. So I would definitely say that in this example right here, that height, I would definitely say in this example right here, that age is your independent value, h is your dependent value. I mean, just think about that realistically. Just think, okay, yeah, your height depends on your age. I mean, I know there's lots of different examples of, of people being really young and being really tall. However, if we're thinking realistically, logically here, yeah, a 1-year-old is probably not going to be as tall as a 2-year-old, and then 2-year-old's not going to be as tall as a 3-year-old, and so on and so forth. You're going to definitely get taller as you age. Those values are going to change. I know they're going to probably level off once you get past high school, but yeah, height is definitely dependent on age, especially when you're younger. Now look at the next example here. We have the number of seats, which is denoted by the letter N in a theater, determines how many tickets T can be sold. So is seats dependent on tickets, or is tickets dependent on seats? What do you guys think of that? If seats are dependent on tickets, then a venue might just sell any number of tickets. They might sell, let's say, A band comes into town and the band says, sell as many tickets as you want. Well, that venue might sell like, I don't know, 10,000 tickets, but they only have 1,000 seats. So they made a lot of money for the band, but the venue definitely does not have enough seats. I would definitely say that the number of tickets is definitely dependent on the number of seats. Otherwise, you're going to have a lot of unhappy people arriving at that venue going, well, I thought I bought a seat, but now you're telling me I can't go because it can only hold 1,000 people. Well, you should have thought of that beforehand. Yeah, I would definitely say that for this example right here, for N and for T, tickets, so I would definitely say that the number of tickets is dependent on the number of seats. You don't want to do it the other way around. If you make the number of seats dependent on the number of tickets, then the venue is going to have to maybe build a new theater, make it a lot bigger, and add way more seats or fewer. Yeah, I would say the way we did it here makes sense. All right, in the last example here, we're looking at shelving, S, needed for the number of trophies you win in your various activities. Is shelving going to be dependent on trophies, or is trophies going to be dependent on shelving? And I would definitely say for this one that shelving, the amount of shelving is going to depend, that's going to be your dependent variable on the number of trophies. So you've got your independent value, number of trophies. You might have a bunch of shelves made in your room, but then there's only one trophy to display on that case. Well, then you built way too many shelves. But if you wait and count the number of trophies you have, you've collected, then you'll know, well, I know how many shelves I need. So the number of shelves is dependent on how many trophies you have, or how big the trophies are, I guess, too. That would depend on that as well. All right, so that does it for functions and relations. So hopefully, by the end of this lesson, you guys have a good idea of what makes a function. And we're going to talk, in the next lesson, we're going to talk about some more things here about what makes a function. But I'm going to stop here for the function and relation lesson. Everyone have a great day. And let me know if you have any questions. Take care.